All right, hello. Welcome to the 12th recitation of this course, which is going to be about graph neural networks. So this is a pretty interesting topic, and here's what we are planning to cover today. So we're going to quickly review what a GNN is, or what's called a GCN, so graph convolutional network is defined as, and then we're going to look at what's called a graph convolutional layer. Specifically, we're going to look at forward and backward paths in terms of what is computed, and then we're going to show you how to write that in code. All right, so let's begin. So what is this thing called graph neural network, or GNN? It might also be called graph convolutional network, or CNN. So if you look at what a convolutional network is, we know that it's used especially in processing images or to extract higher level representations out of images, right? It has these nice properties as, shift invariance, and then the kernels that are very useful in that you can detect the feature wherever they're in the image. So then the higher level idea is that you can use a convolution to extract patterns out of not just pixels, but groups of pixels, right? So the idea that is also applicable to graph neural networks is that, graph is a pretty useful data structure, right? I don't need to make that point. So it turns out that if we need to get the higher level representation of a graph node, then what we do is also just to take, just like how we do the convolution on the image, which is to take a convolution of an image and its neighboring a pixel, and its neighboring pixels, and then get some sort of, weighted combination of the values stored in these group of pixels. We do that same for nodes, right? So we know on a graph, each node has a bunch of neighbors, right? So it turns out that the motivation is to learn the higher level representation of a node or the features of a node by aggregating the information contained in its neighbor nodes. All right, so it's kind of similar to what we do in CNN to the pixels. So a key feature, a key property of the graph data structure we notice here is that the graph is solely defined by what the nodes are and what their neighbors are. Okay, so that's all the information contained in the graph. There's no other thing. So here we have an example of a graph. Right? So let's just take the node B in here. If we want to get an embedding for the node B, what information does it contain? Of course, it contains all of its neighbors, right? So we have the three neighbors of B, which are A, C, and D. So just like a generic neural network process, what we do is we take these three neighboring nodes, so A, C, and D, and we have some sort of also, right, we don't want to lose information from itself. So for these three nodes, it turns out that we can also use the convolved representation of these three nodes, right? So what does A mean? So like, what information does A tell us? A itself is the result of a convolution of, say, its neighbors. So that's going to have both A itself and then B, because we said before, we agreed that, the information from B itself is also going to be part of the convolution that goes into the higher level representation of B, right? So here we further expand the computational path in that, okay, B takes in information from A, C, and D, and then A in turn takes information from itself and all its neighbors, which is just going to be A and B, right? So C takes information from itself and all its neighbors, which is going to be C, B, and D. And D takes information from both itself and its neighbors, which is going to be D, and then B, C, E, F, right? So this is how we get, if we take a degree of 2 in the convolution, then we have the final representation of B taking in information from B, A, C, D, which in turn takes in information from all these nodes, right? So we talk about this process, which is almost like a black box, right? So when we say that B takes in information from A, B, C, D. What does that mean? Like, how does information get combined? It is sort of like a black box, but it turns out that just like the generic neural network process, this is very applicable. Just as like we can take what we're doing in just like neural networks in general and put it here in this idea of applying it to graphs, right? So we take the ACDB in neural networks. If we have a linear layer, we apply some sort of linear combination in the inputting features, and then we apply some sort of nonlinear activations that make the network interesting, right? So we can do the same thing here. For the A, C, D, and B, so the input features in this network, we can do some sort of, ordinary operation, which is going to be, either add them up or taking the product or even taking some, hyperdata like taking the mean or the max or min, etc., right? So that we have some sort of primary or primitive combination of these features. And then we apply some activation, which is going to be the step 2 here. And here it says apply neural networks, but then you can just apply any nonlinear activation to make this interesting, right? So the traditional approach is usually just to take the mean. That's brought up in this paper over here, and that's just like, if you're not sure what to do, you can think of the mean as, just unbiased combination of all the information in those data cells. Okay, so here comes the question: how do we write out the value of B given out by this process, right? So it turns out that this is the complete rendering of this process. Don't be afraid, we're going to walk over this formula side by side, step by step. Okay, so here, let's first clean out some dimensions of things brought up in this formula. So what is meant by h of v of t plus 1? So this means the representation of the data node v in particular at time step t plus 1, right? So h of v of t in here that I'm putting my mouse over means the representation of the node v at time t, right? So this is telling us in order to compute the next time step representation of the node v, we need to use this formula, right? And then this middle term here, h of u of t, is just the representation of u at time t. Okay, so at this point, I've talked about the representation of data nodes, but what does that actually mean? So in here, we're just going to define that each node is being defined as a vector, right? Specifically, it's being defined as a 1 times f vector without loss of generality, right? It could be an even more complex data structure, but in the end, you can store an arbitrary amount of information in a vector that you can define the size of, right? So in here, we can see that the entire H matrix that contains the entire representation of all the features in all the nodes I'm putting my mouse over right here. So it is an n times f sized matrix. N is the number of nodes in the graph, and f is the number of features that comes with each node. So you can see that in this matrix, you have n nodes, so A, B, C, D, E, F. Since we have 6 nodes in the graph, this matrix is 6 times f. Each row is representing 1 node, and each row contains f columns because each node is a 1 times f row vector that contains f numbers in them. Okay, so this is how the H matrix is defined. It defines the entire feature representation of all nodes in the graph. All right, so let's decompose this. Okay, so the first component of this complex formula we have here is the summation over all u in the set of neighbors of V. Okay, so this is what it's defined as. N of V just means the neighbors of V. So the nodes that V has a direct edge with, right? So when you look at this part within the red box over here, it means that you take each neighbor and you take their representation, or you take their features and you add them together, but you divide that with the number of neighbors, right? The size of the set of neighbors of V. So it is just an unweighted average of all these neighbors. That's all it is, right? Just look at this. Take all the neighbors of V, add them all together, but divide it by the number of neighbors. So that is just an unweighted average of all the representation of neighbors of V. So it also turns out that we want to do everything in matrix multiplication form because that is said to be more efficient, right? So how do we do this? So first of all, we look at the right mode matrix in here is just the feature representation matrix, right? We talked about that just a while ago. And the middle matrix here is what's called the correlation matrix or the neighbor matrix, in that you can basically think of each cell in this matrix as either white or blue. You can think of it as being even a binary matrix with values being either 1 or 0. And a 0 here, which is, I think it's colored white here, means that they are not neighbors. And a blue cell would mean that they are neighbors, right? So you can see that B and A are clearly neighbors. And for some reason, B and B here, they're not colored as neighbors, because in usual, the mathematical graph convention, a node is not a neighbor of itself unless there is an explicitly defined edge, right? But that doesn't matter. So the neighboring matrix just tells you which node are neighbors of which nodes and which are not. So it turns out you can also assign values to edges. So that's why in this graph we show different colors or different shades of blue. But then, for simplicity, you can just think of it as being either 0 or 1, right? 0 as being not neighbors and 1 as being neighbors. Okay, so we take this neighboring matrix and we multiply it, or we do matrix multiplication of this neighboring matrix with the feature matrix, right? So the neighbor matrix is certainly n times n because there are n nodes, and you want to take the relation of each node onto each node, right? So you have an n times n matrix, and the feature matrix is an n times f matrix. So then when you think about what happens in here, when you take the neighboring matrix with the feature matrix and you multiply them, what happens is, let's take the resulting matrix. It's definitely an n times f matrix, right? So the first cell, meaning the first row, first column cell in the resulting matrix, what does that tell us? That's going to be the result of the first row of the neighboring matrix and the first column of the feature matrix, right? So the first row of the neighboring matrix, it tells us what cells are neighbors of A, right? We're looking at A over here. And the first column of the feature matrix tells us what's in the first dimension or the first feature of each cell or each node, right? So that is basically giving us a combination of the first feature of nodes that are A's neighbor, right? I hope I made that point clearly. So the first row, second column cell in the resulting matrix tells us it is a combination of all nodes of the second feature of all nodes which are A's neighbor, right? So in general, the ith row, jth matrix, the ith row, jth column entry in the resulting matrix is going to be a combination of the jth feature of nodes that are the ith node's neighbor. All right. So that is the general definition of what we have when we take the neighbor matrix and the feature matrix and multiply them together. And then we have in the leftmost, we have this diagonal matrix, which is nothing more but you have 1 over the number of neighbors on the diagonal. So then that does this unweighted average thing over here. So you time this onto whatever we have, then the resulting matrix will have all the values divided by that number on the diagonal. And I know that matrix operations are not commutative, or you can't flip the order of combinations, but then this diagonal matrix doesn't really matter how you put it. So that's the order that I choose to explain this in. Okay, so now we have this. We notice that the result of multiplying these 3 matrices together is exactly what we have over here, right? So that is taking the neighbors of node V, adding them together, and then taking the average, meaning dividing the sum by the number of neighbors, right? So the resulting matrix, each row represents a cell, and each column represents a feature, right? So in the resulting matrix, each row, there are still n rows, and then each row still has, each cell basically lives in a 1 times f feature vector. The only difference is that in each of the f cells in a certain row, that cell now contains aggregated information from all its neighbors, right? I think that should go pretty clearly. So after that, we also multiply this result with a weight matrix, which is denoted by WK over here. You know, why do we have that? We just want weights to this variable, right? Because that gives us some room to learn stuff. Because up until now, everything is set in stone, right? It's defined by there's no variable. They're all defined by the graph. So the weight matrix gives us some room to finally learn stuff. And the weight matrix is going to be an F times F matrix. That's going to come last in the chain of computation to make dimensions match, right? So if you look at, we have n times n, the diagonal matrix, and then we time it with n times n of the neighbor matrix, which is also just going to make it n times n, and we multiply it with n times f, which is going to give us n times f, right? So finally, in order to have an n times f result, we time that with f times f, right? So this weight matrix, when you have the dimension of f times f, you should understand it as you are taking the relation, you're having weights for each feature, or you're having relation from each feature to each feature, right? So that should be pretty easy to understand. So the question is, why do we put WT on the right-hand side of whatever we just had, right? So the feature representation that we calculated. Why not make it on the left side, which would look like this, which would also make dimensions match, right? So if we take the n times n weight matrix, that's different from the f times f weight matrix we proposed here. If we take it to be an n times n weight matrix instead and multiply it with the n times f representation matrix, that will still make dimensions match, right? So why don't we do that? The problem is that if we did that, then think about what is contained in the first cell that comes out of this matrix. The weight will be distributed over the same feature, but in all nodes, right? So instead of having, so if the weight was put on the right side, then the result of this computation, the first cell, meaning the first row, first column of the resulting matrix, that cell contains a weighted average of all the features in node A, right? You take the first row, which is node A, and then you take the first column, which is the first column of weights. So that means you have a linear combination of all features in node A, right? That's what we have in the first cell in the resulting matrix. But if we had instead put the weight matrix to the left of the feature representation matrix, then what the first cell contains is a weighted combination of all the first features across all nodes. So that is no longer a representation of node A. That is a representation of a combination of cells, of a combination of nodes. So that is wrong because we will not have a representation of the graph after this operation, right? So remember, the central goal for us to do this complex expression over here is to be able to have an updated and more aggregated representation or even embedding of a certain graph, right? That's our goal. And having a representation of a graph means having a clearly defined representation for each node, right? That's the only way you would have a representation of a graph. And if we instead had put the weight matrix back to the left of the feature representation matrix, we will not be able to have a clearly defined representation for each node, right? Because as I said, each cell in the resulting matrix will have a mixed representation from all matrices. And that is different from the step we took a couple steps back when we aggregated the information from neighbors, right? That step also takes in information from different cells, but that was intended because each cell wanted to take in information from its neighbors. That's why we aggregate, that's why we do convolution on graphs. But then that step, that taking in information from neighbors shouldn't happen in this step of applying weights to matrices, because the weights is not a means by which we aggregate graphs. The weights is simply a post-processing step that we apply to what would otherwise be already a good representation of a graph, just to have some room for learning stuff, right? That's why we have weights. We have weights for room for learning. We don't have weights for aggregating information from neighbors. So that is why we don't mix information among different nodes at this step. And that's why the weight matrix is best put on the right side of the feature representation matrix instead of on the left side. Okay, so this is just an illustration of why we have to have a clearly defined representation for each node that makes our representation ready for more downstream processing, like feeding into a linear layer. Okay, so yeah, the weight matrix placement is different from what's written down in our formula, but then here it is. So here is the complete picture of the left side of this formula, of this expression, which is we aggregate the information from all the nodes neighbors, we put them together, take the unweighted or weighted average, and then we multiply that with a specific weight matrix. So that is the updated representation that contains the neighbor information. And then it turns out that it will also be good. I mean, you would think about, if we're taking the neighbor's information, why not take in the information from this particular cell we're dealing with? So we can do that. And then that basically means doing the neighboring step all over again, basically just doing that step. But then for the neighboring matrix, we're just going to define a neighboring matrix with each cell only being the neighbor of itself, right? That's very straightforward. So then what you have as the neighboring matrix is this diagonal matrix over here. You can think of the diagonal as being 1 and non-diagonal elements as being 0. So basically an identity matrix. And you multiply that with the feature representation matrix, just like in the neighboring, just like in the last step in here, you multiply this neighboring matrix with our feature representation matrix, and then you time a weight matrix, which lives under the name B in this time step, right? But they're all the same. They're just weight matrices. So it's the same. It's the exact same as the last step, which is the neighboring step, which is the step we gather information from neighbors. But then the difference is that we don't need this this diagonal matrix with which we scale down the values, because in here we only have one value coming from each node, so we don't need any additional scaling over here. So in here we just get a weighted combination of each cell's own values or own feature values, right? So what we do is we take the result of this first step, which contains the information from neighbors, and the results from this second step, which contains information from itself. And since these dimensions match, right? So notice that this step produces a matrix of n times f. And the last step, this step, also produces a matrix of n times f, right? So it turns out that these dimensions match, and we just add them together to be a large matrix of n times f. And then we apply some sort of nonlinear activation to the resulting matrix and call that the next time step representation of this graph, right? Since this matrix has n entries, it is no longer if we represent it in vectorized form, then the entire matrix is not just about a single node, it's about the entire graph, right? So we write it with capital letters. So this thing basically contains two parts: the aggregating the information from neighbors and aggregating information from itself. Put these two together, nonlinearity, and then we have the next time step representation. So up until now, it should be pretty clear what we've been doing, right? So it turns out that since, when we take a look at what we've been doing, in this time step, the neighbor, or in the neighboring matrix, the diagonal is completely empty, right? Because we specifically defined that each node is not a neighbor of itself, right? And in this step, in this component of our operation, the diagonal is lit up, but the non-diagonals are completely empty because we just want to take the diagonals in here, right? So these two time step, or not time step, but these two processing steps do not interfere with each other. So the operating field of this component is going to be completely zero in here, and vice versa, right? So with that in mind, we can combine these matrices. We can combine these two components and make them just a single component, right? So what we can do to achieve that is we take the neighboring matrix from the and we add these two neighboring matrices together. So we have a final, what we call A hat. We have a final neighboring matrix where each node is a neighbor of itself, right? So that's a combination of the two separate neighboring matrices that we've been building, and then we put that in place into the original equation in the neighboring step. And with the same setting in mind, we can also aggregate the two different weight matrices together because their shapes also match, right? So we call that W prime, and the HT really is not that much different from across these two components, and the D-1 is just a regular constant matrix. So that is how we can combine the two formulas, or the two components of our convolution operation together into just a series of matrix multiplications for a single component, which is going to make things a lot cleaner. So that is the forward equation for graph convolutional network. Take a second, pause the video, think about whether you have understood this entire formula. The story is that we start with a representation of the entire graph, right? Think about H. H basically means the representation for an entire graph because it has n rows and f columns, right? So we start with HT, means the representation of the graph at time t, and we arrive at H of t plus 1, which is the representation of the graph at the next time step. But then in this next time step, hopefully, each node is better represented, or each node has a better embedding in the vector space because they take in information from both themselves and their neighbors. And as t grows, meaning as we progress into more and more time steps, their neighbors also contain information from their neighbors. So each cell would have, hopefully, all the information from the entire graph, which is going to make it rich represented and definitely more useful than just containing the number on its own, right? So that's the forward equation for graph convolution network, or GCN. And then we can think about what is the backward pass, right? So in order for us to devise equations for the backward pass for GCN, let's first recall some mathematical, let's have some background, let's warm up. So if we have a matrix Y being the matrix multiplication of X and W, so the @ sign here, I've just used NumPy notation to use the @ sign to denote matrix multiplication. And consistent with NumPy conventions, the element-wise dot product is just written as a star sign, or just the normal sign some people use as multiplication. That's the dot product or element-wise operation. So here, let's make a toy example, right? Y is the matrix multiplication of X and W. Let's say that Y is 4 times 2, and X is 4 times 3, and W is 3 times 2, right? So if we have a loss of, we have a loss and we have the derivative of the loss with respect to Y, how do we get to the derivative of the loss with respect to X and W? So taking the loss of X, of L, the loss with respect to X turns out to be pretty easy, because, you know, dl dy, and we take dl dy and dy dx and we time them together. That gives us dl dx by chain rule, right? That's very easy. So it's basically, so dy dx, remember that if y is x times w, then dy dx is just w transpose. And we take a sanity check in here to check the dimensions. So dl dy is the same dimension as y, right? So that's 4 times 2. And what is the dimension of w transpose? Since w is 3 times 2, w transpose is 2 times 3. So this works out to be 4 times 3, which is the same dimension as x. So that's why we can be confident in that this is probably correct. Okay, so what about the LDW? The LDW would not be so simple because it is not convenient to take derivative with respect to the second parameter in the matrix multiplication. So instead, we take the transpose of y, and it turns out that the transpose of y is just w transpose times x transpose, right? Because transpose can be used to flip the order of operands in matrix multiplication. So if we take the transpose, w transpose suddenly becomes the first operand in this multiplication here. So the L, the WT, we can take in the normal method, right? So that's going to be DL DYT times X, right? This should come as no surprise, and I've had the derivation steps written in here. So if we have DL DWT, how do we get to DL DW? It turns out that DL DWT, so DL DW would just be, you know, the transpose of the transpose of the LDW, which is just going to be the transpose of the LDWT. And then that's how it's written out. So we take a second again to check the dimensions. So DLDYT is going to be the same dimension as Y transpose, which is going to be 2 times 4, right? Because the original dimensionality of Y is 4 times 2. This is 2 times 4. And then X is a 4 times 3 matrix. So these two things multiply to be a 2 times 3 matrix, right? And we take the transpose of the result of this multiplication. So that gives us this 3 times 2, which is the same as the original W. So we know that this is probably correct. Okay, so once we have understood these two, we can call them corollary, right? We can name this DLDX our first lemma, and our DLDW our second lemma, right? So these things are going to be useful later on when we are calculating the actual backward equation for our GNN that we defined before. So just have these two lemmas in mind. Okay, so now let's get to derive the actual backward equation. So how should we define it? Remember that this is what we said it's going to be our forward equation, right? The h, or the representation of the graph, h at t+1 time step is going to be an activation of the multiplication of these four vectors, right? And the dimensions match over here. So before we get to the actual derivation, let's define a few terms for the sake of convenience. So let's define h tilde as these four terms. So basically what's inside the brackets, okay? So let's also define h0 of tilde as the last two terms. And the reason for that is in this four-term multiplication here, the first two terms are frozen in that we don't change those, right? So d-1 is defined by the graph itself. It just contains the number of neighbors for each cell. And a hat, as we discussed before, is just an augmented neighboring matrix, right? That's also defined by the graph, and we don't change that at all. So it is, we're not interested in taking the derivative with respect to these two matrices. We're only interested in taking the derivative of loss with respect to ht prime and then w prime transpose, right? So we're only interested in taking the derivative with respect to the later two. So we group them together under the name h0 of tilde. And we want to derive these two derivatives. Okay, so with these definitions, let's first draw out the computational graph, because that's how you do derivatives, especially with tricky things like matrix multiplication. So this is the computational graph. You have ht prime and w prime transpose. You time them together to form the term that we defined manually, which is h0 of tilde. And then you time that with d inverse and then a hat, and then that gives us h tilde, and then we apply the activation in here to give us the final h of t+1. Okay, so this is the forward pass direction of the computation. Now let's get to the backward. Let's do it reverse. So the first thing that we notice is that the dld h tilde is just going to be dld h t+1 dot product the ht+1 the h tilde. And why is that? That's because the only computation that happened between h tilde and t+1 is the activation on this arrow over here, right? So you can just take the backward of the activation in here. And then dl dh0 tilde is going to be this expression. So basically we take the derivative of L with respect to h tilde and we multiply it with d inverse a hat, and we use the second lemma that we defined before, right? So remember that h tilde is the result of multiplying these two matrices. We just use the second lemma, which is used to define the derivative with respect to the second component of a matrix multiplication from just now, right? So let's now also recall that h0 of tilde is the same as the multiplication of these two matrices in that order, right? So the final targets that we're trying to attack over here, so the dl, the ht prime, we use basically the first lemma, right? Because ht prime is the first component of this matrix multiplication that gives us this matrix. So we just apply the first lemma. You can scroll back to find out what the first lemma is, but then that just gives you this expression. And then dl dw prime transpose, we use the second lemma to get from dl dh0 tilde to here, right? So since we already have gotten dl dh0 tilde, we just apply the first and second lemmas to get us to ht prime and then w prime transpose. So this is the equation for the HT prime and then W prime transpose, the only two matrices in this whole process that we have room for learning, meaning that these are the matrices that we change, right? So only because they change, it is meaningful to take the derivative with respect to them. Otherwise, the derivative is going to be zero, right? So here we are. We have gotten the backward we have gotten the backward pass equation for the graph convolutional network. So then, just to look back, what we've covered is we've covered what a GNN is, we've covered what the convolutional operation is, what it does, and how to compute the forward pass and how to compute the backward pass mathematically from a matrix multiplication vectorized point of view. And then starting from here, we can show some code that actually implements some of that.
Hey everybody, so let's move to the coding section of this recitation. Here I'll be trying to walk you through how exactly you can use PyTorch geometric to implement graph neural networks for two tasks, one being graph classification and one being node classification. Right, for the graph, Hey everybody, so I'm going to walk you through some of the code that we can use to implement graph neural networks. We will be using a library called PyTorch Geometric, and we will be working with primarily two tasks with graph neural networks, one being graph classification and one being node classification. As you can see the diagram right here, for graph classification, the input is an entire graph and you get one label. For node classification, you will get a graph with a bunch of nodes. For each node, you would have to come up with a label prediction. So here you might have multiple graphs as input. Here you would have one huge graph as input where you would have to label multiple nodes, right? And as Josh has already explained, some of the theoretical concepts, we'll be trying to understand how to implement those with graph convolution layers using PyTorch geometric. So first things first, we'll work with the graph classification task. This uses the molecule net dataset, right? The goal is to basically predict what the solubility of a specific molecule would be, right? Right here, we're trying to load the dataset. You can see that we have around 9 features per dataset. You have, for example, you have 32 nodes and 68 edges for a single molecule, right? And these are some of the this is basically a visualization of how exactly the molecule actually looks like using the RDKit library. The way this is stored is using the SMILES notation, which is basically a fancy notation, string notation to represent these kind of graphs, like as you see over here. But the goal is to basically convert this to a graph notation using the PyTorch geometric dataset class that they've given us, and try to see if we can use a graph convolutional network to aggregate information that is available to us from these graphs to understand what its solubility would be. So it's kind of a regression task, if you will. So as you can see here, we have a graph convolutional network here, right? Clearly, the idea behind graph convolutions is the concept of message passing in graphs, right? How do you exactly aggregate information from neighboring nodes? A simple concept is the weighted sum, as we saw. You just get a weighted sum of the neighboring nodes features. You use a linear transformation where you pass the input nodes features using a learnable weight matrix. And then you kind of add it along with these message passing and aggregation of the features that you get from the neighboring nodes, right? Before that, obviously, you have the pre-processing step as shown here. Basically, you add self loops and normalizing it using node degrees, right? As you saw in the equations that Josh presented. So right here you have a bunch of convolution layers, right, with the embedding size being 64, and then you have a final linear layer, and in the forward function, we basically take in the edge index and the batch index. We do the initial convolution with a tanh activation first, right? Obviously, for the convolution to happen, you need to take in the edge indices for that specific graph. because that's how you basically aggregate information around all the edges that the input node is connected to. You basically pass it through these convolution layers and activation layers, and then you usually do a global pooling, right? Basically, finally aggregate all of these features that you got from these convolutions together, and then finally project it as you would in a regular image, right? As you did in homework 2, the goal was to basically pass your image through a bunch of convolution layers, pull it down, and then project it to a number of classes. That's basically the exact same thing we're doing here, except the convolution layers are graph convolution layers using PyTorch geometric. So right here you can see that we're using the MSE loss. The reason for this is because we're trying to predict the solubility of the molecule, which is a real valued continuous number. So that's kind of why we're using MSE loss as our criterion. We're using the Atom optimizer, and we're splitting the dataset into 80 to 20% splits. Yeah, we're basically iterating over each batch, getting our prediction using the same principle that we've used in all the homeworks. And we're training it for 1,000 epochs right here. And as you can see, the loss continuously decreases. There's a little bit of fluctuation towards the end, but that shouldn't really matter. The next goal is to obviously try and see how we can visualize these predictions that we get. So we get these predictions, and as you can see here, we put it in a data frame so that we can understand what the difference is between these. You can see there's some variance right here, but a better way to visualize this would be to plot it down for these test samples, right? And as you can see here, a perfect prediction would involve a straight line, right? All the points being in a straight line where the actual y is also equal to the predicted y, but you can see there's some variance. But overall, you can see that the line has a decent fit, right? The loss values are shown here. As you can see, there's pretty much of a fluctuation, but a overall decreasing trend. So moving on, we're going to go to the next task at hand, which is node classification. Right here, instead of having multiple separate graphs, such as molecules, we have a single extensive graph. And the dataset we're trying to work with here is a citation network, right? Where nodes represent documents. Each node is described by a 1,433 dimensional bag of words feature vector, right? So two documents are connected if there exists a citation link between them. The task is to infer the category of each document. There are 7 categories in total. And that's kind of the data set we're going to be trying to work with here. So for the Cora data set, this is called the Cora data set, by the way, you could still technically use the bag of words feature representation with a regular MLP and try to see if you can predict the category, right? There's 7 categories in total. But obviously, this doesn't really work very well because you can't utilize the citation information that's contained between these nodes, right? You can't just use the bag of words feature vectors, and they're not going to give you the maximum information as to inferring the category of these without understanding what the links are between these nodes or these papers. So these publications, I mean, the citation links can be valuable information that you may be able to infer only using the graph structure as opposed to, say, using a bag of words representation alone, right? So GNNs can exploit these relationships, and that's kind of why graph neural networks are powerful in the areas where you can exploit relationships between unstructured data, using a graph-based structure, right? So here are just some cells to show you how the labels look like. So in a node classification task, you would have to have binary masks that tell you what nodes are actually labeled nodes for training and what nodes are test nodes that you have to infer from. That's kind of why these masks exist. So they're just Boolean masks that tell you whether that node is part of the training set or the test set. Again, we're just using a simple graph convolutional network. Here, we don't really have to worry about pooling because the goal of the task is to basically try and see if we can project these convolution features to these number of classes. So you have a couple of layers that have convolution layers, and then you have an output linear layer. You have a bunch of activations and some dropout. So again, we go through the same process. Right here, I've included some weight decay for some regularization. We have train and evaluate functions. Right here, as you can see, we check against the ground truth labels using the masks that's part of the data set, right? So we check whether the test mask or the predicted logits for the test nodes match the ground truth variables for the test nodes, right? And as you can see, training it for 1,000 epochs gives us a pretty stable decrease in the loss over to 1.16. Loss has a stable decrease below. So that kind of basically sums up how exactly these graph convolutional operations or graph convolutional networks work for 2 types of tasks. There are more tasks out there. You can build recommendation systems with graph neural networks. I would recommend going through some of the resources available online. Distal.pub has a amazing resource explaining, basically tackling the open exposition problem of explaining graph neural networks, and 2 posts, really detailed posts. I recommend you go through them. It even has a playground where you can fiddle with graph neural network representations. I also recommend going through DeepFinder's YouTube channel. A lot of what I've covered also draws from his channel and the resources that are present in the Python geometric repository. So I would recommend going through his channel as well. He has some fantastic resources and project descriptions for graph neural networks with some literature analysis. And with that, I would like to conclude this recitation. Hope you all understood and can play with this notebook. This notebook will be attached in the description as well as the course website. Feel free to play around with it and reach out with doubts or clarifications if you have any. Thank you.